Right. October 25th, 2019. This building was built in 1952, or any of and God knows what will happen, you know, in another 67 years from now, whether IES will still be standing. I expect it will. But this is the last class that we can be taught in this building, so welcome to history.
Did you miss here?
We'll miss some things. I think there are things already people miss about this building. But you know, I've lived long enough to realize that everyone is a conservative. People don't like change. Change is hard. So in a little bit we'll say, oh my God, you remember living in that rat-infested thing called an astronomy out there on the other side of campus? So we'll get over it pretty damn quick. All right. So let's see. Let's quickly recap where we were at. We're getting some basic ideas about quantum fields, and to do that, we're looking at this toy problem of a 1D scalar field, which, as an example, we're thinking about as the field associated with the motion elastic waves on a 1D rod, whose Lagrangian is described here in terms of the field amplitude beta at some position as a function of time along the rod. Okay? And what we showed is that the Euler-Lagrange equations for this, given that Lagrangian for the field is nothing other than the wave equation in 1D with a certain phase velocity depending on the Young's modulus of the mass density. And then what we did is we said, well, we're going to look at particular solutions that are separable in time and position, and those are what we call the normal modes of this wave. And that gives us this equation for the spatial distribution of the mode. Okay? And ultimately, what that mode is will depend on the boundary conditions. So there are two typical cases that we look at, so-called hard wall boundary conditions, where the wave amplitude is pinned to be zero at the boundaries, in which case those modes are the standing wave modes. Or we think about periodic boundary conditions, as in thinking about the waves on a ring here, in which case we have traveling wave solutions that can be traveling either clockwise or counterclockwise on this loop. Okay? And the reason that by putting boundary conditions on in the system, that discretizes the allowed modes into a countable set of modes. That's just, I mean, as we will see, you know, there's different circumstances. In one case, those boundary conditions can be artificially imposed as a convenience, as sometimes what we call a quantization volume. In this case, a quantization length, to give the rod a finite length, because it allows us to do the calculations more easily, and then take the limit as L goes to infinity and put those boundaries at infinity. It's a kind of computational trick. sometimes those boundary conditions are real, right? We might, as we will be talking about very soon, thinking about, for example, an optical cavity where we have two mirrors and we have Fabry-Perot-like modes of standing waves of the electromagnetic field between mirrors. So sometimes those boundary conditions are physical and sometimes they're there as a mathematical influence, okay? But once we do that, that allows us to express the field in terms of a countable number of degrees of freedom, okay? It's still infinite. There's some infinite number of modes, but it's countable in this way. And once we've done that, it says, because these modes are a complete set of functions on the line, these are a basis of functions on the line, of square normalizable functions on the line, we can decompose the field at any time as a superposition of those modes with some coefficients that depend on those times. And those coefficients are just the what we call now the coordinates of the field with respect to that mode basis set. Okay? And those, in the case where there's no other interaction, so this is the free field, like, you know, I'm not hanging a pendulum off this thing and letting that interact. So this is just the equation for that field interacting with nothing else other than the boundaries. Then the equation of motion for the coordinate is just that of a simple harmonic oscillator. Okay? So as if we showed, if we substitute this mode decomposition into the wave, into the Lagrangian, then we get the Lagrangian is nothing more than that for a set of simple harmonic oscillators. Okay? And thus the corresponding Hamiltonian for that system is the Hamiltonian for the collection of simple harmonic oscillators. So the lesson that we take away from this is that we can think about the degrees of freedom of the field as the modes. Each mode is a separate orthogonal degree of freedom. That's how we mean it to be a mode. If it's an orthogonal, any orthogonal decomposition we call a mode. We call it a normal mode if it's a harmonic oscillator, but any other decomposition would be a perfectly fine mode decomposition if it was an orthonormal set of functions on the line. Okay? The normal modes are the ones that are normal. They oscillate with a fixed frequency. And each one of those, if it's a normal mode, each one of those normal modes is a harmonic oscillator. Okay? So with that said, what we did at the very end of class is we quantized it. And the way we did that was like this. Again. So each normal mode is now a quantum simple harmonic oscillator. And from that, we said we can write the Hamiltonian in terms of the characteristic energy, in that case, h bar omega, relative to my dimensionless coordinates, the quadratures of the mode, which is equivalent to where the number operator is a dagger A for that mode. This is for a given mode, P, X sub k, and P sub k. X sub k here is the coordinate in units of the characteristic length scale for that mode. P sub k is the momentum divided by the characteristic momentum for that mode. And A is X plus IP over root 2, where the characteristic scales are the square root of H bar over M omega, and momentum characteristic is the square root of M omega H bar, right? For that harmonic oscillator. Right? And moreover, different degrees of freedom commute. Right. So, one thing I just want to mention, because there's going to be a variety, notice that these things that look like position and momentum are properties of the field, right? These were the quadratures associated with a harmonic motion that represented the amplitude of cosine and sine, right? This is not, as we will see, related to the position and momentum of the phonon. That's a totally different thing. They are the quadratures of the field. They are field degrees of freedom. They're not particle degrees of freedom. We're going to come to that in a moment. Okay? This is not, this harmonic oscillator is not the harmonic oscillator of a particle in a trap, right? This is the normal mode oscillation. This is in some sense a particle in a box, not a harmonic trap. It's confusing. Think about that a little bit. In a moment, we'll come back to the particle aspect of this, which we haven't really touched on. Now, I do want to mention, okay, so before I do that, let's write down the quantized field, okay? So now I have the quantum field, and this is thought about typically in the Heisenberg picture. Not always, but typically. So in the Heisenberg picture, the operators are evolving as a function of time. I can do it, and we often sometimes do. We sometimes do it. Often, if it's often. Write it in the Schrodinger picture, and this would be time independent, but right now I'm discussing it, the free field in the Heisenberg picture. Okay. So this is equal to, let's say for the I'm going to say here for hard wall boundary conditions. So this is equal to the square root of L times the square root of the characteristic length scale squared. Just write it like this instead of putting that inside there. And then I have the sum over the modes. I have AK plus AK dagger over root 2 So this is the position as a function of time, right? Which is a of t plus a dagger of t over root 2. That's this, right? So this is equal to, when I put all that in, the square root of h bar and over 2 mu L ak sine kx e to the minus I omega sub kt plus the complex conjugate or Hermitian conjugate. All right. If this were periodic boundary conditions, this would go to this, and this would become the conjugate. So generally speaking, we can write the quantum field operator as some characteristic scale ak of t uk of x plus the conjugate. All right. If I were in the Schrodinger picture, this would be fixed in time. In the Heisenberg picture, these evolve in time, and if in free field, they evolve like e to the plus I omega t or e to the minus I omega t. Okay. All right. Very good. Now, come back to this in a moment. So, these are the operators that describe the Hamiltonian, the quadratures, the fields, etc. What is the Hilbert space that we're talking about? Well, this is the Hilbert space, in this case, as we have written this in terms of the modes. What we have is a collection of harmonic oscillators. So I can think about the Hilbert space if I allow myself arbitrary excitation. My Hilbert space, which I'll call script H, is equal to the tensor product over all the modes, the Hilbert space for the kth mode. Well, what is the Hilbert space for each mode? It's an infinite dimensional Hilbert space, which we can think about as the space of square normalizable functions on the line. If we have a finite length, it's between 0 and L. So our mode functions represent basis functions of that kind of Hilbert space. What is a basis of this Hilbert space? Well, one basis is what we call the Fock states. The Fock states would say I have, in each harmonic oscillator is the product basis. So for each product of each k, nk, where nk can be 0, 1, 2, up to infinity. So we would typically write this as some number of excitations in mode 1, some number of excitations in mode 2, etc. Right? So if we had a collection of harmonic oscillators, for example, if we had two masses connected by a spring, we can think about the number of excitations in the symmetric and the antisymmetric modes. Those are the normal modes of my two masses, and each one of those would be quantized, and I'd have some number of excitations, the harmonic ladder. This is what we call the Fock states, and this kind of Hilbert space we call Fock space. So it's a little bit of a weird notion. Actually, any superposition of these is also in the space. You might call that also a Fock state, but it's become tradition to call the number states Fock states, and anything else a superposition of Fock states. But I had a professor who hated that. He said everything in this space is a Fock state because it's Fock space. So, what is these states? These states are eigenstates of the Hamiltonian. Right? What is the eigenvalue? Is everyone clear what this label means? This is for the first mode, the second mode, etc. If this was, say, hardwall, they would be, if I could have plus or minus 1 depending on if I had a traveling wave modes, whatever I'm calling modes. So what are the eigenvalues? Sometimes we write it like that. So for the set of all, so this is the set N1, N2, N3, all the occupation numbers as we call them. What is the eigenvalue in that case? Exactly, so I have right there. There's my, so I sum over k, h bar omega sub k, and k plus a half. Now it's kind of problem here. Anyone see a problem with this expression? Yeah. The half, right? I mean, this is equal to sum over k, h bar omega k times nk plus a half sum over k, h bar omega k. But this is what? It's infinity. What the heck can we say about that? I mean, when we had one harmonic oscillator, and that harmonic oscillator had a 0-point energy, there was some amount of energy associated with the particle in a well in its ground state. We're used to the ground state having some finite energy above the 0 potential. But if I have an infinite collection, even if it's a countably infinite collection, then I have an infinite amount of 0-point energy. Do I care? Do you care? What do you think? Yeah, I'm listening.
Can you cap the number of modes? Can you say beyond such and such mode, those modes are
That's
not.
a good point.
So
So
the
that's one
problem
solution, to say that there's got to be some cutoff here. That somehow the sort of the minimum wavelength of the universe at the Planck scale or something where strings happen and, you know.
I don't know what that limit should be.
Yeah,
There should
yeah.
be some chaos.
Yeah, I think that's
now it's finite.
reasonable. And I think we all would agree that there's some kind of absolute minimum wavelength scale that over which this thing max, so there's some K max. But that scale can still make this term huge. Do we care that that's huge? Do we care that it has any value at all? Well, it depends what you mean by care. It does not affect anything relative to the dynamics, because this is whatever we're calling the ground state of the system. This is the energy of the vacuum state. So the vacuum is the state which we call zero, which is all these guys being zero, no excitations in any one of the modes. That's the vacuum, right? And the energy of the vacuum is this. That's the ground state of my field theory. And as we know, the equations of motion, anything we would calculate in terms of the probability of any outcome, doesn't depend on what the absolute energy is. It only depends on the energies relative to what the ground state energy is. It could have even been infinity. I wouldn't really care from the point of view of the dynamics. But there's still a potential problem in that there is one place where the absolute energy matters, not just the relative energies relative to some reference point. And where's that? Where in physics do I care what the actual absolute energy density is? Yeah.
GR.
In GR, right? Because the gravitational field depends on the actual energy density. So it's a big question. What is the effect of the vacuum energy on GR? It's one of these things I really don't understand what the common wisdom is on this. You know, when I hear talks about things like dark energy, I'd say, and I've asked some of our colloquium speakers about this, but I've never gotten this, I'll tell you what I've heard as the answer, is how can we possibly believe we have any solution and understanding of what might the origin of dark energy might be if we don't have a quantum theory of gravity? Because don't we care about the quantum fluctuations? And if I'm going to think about a quantum theory, don't the quantum fluctuations of the quantum field somehow come into this whole question about the cosmological constant? And because as you might say, this contributes to the cosmological constant. And the answer I get is, well, I've gotten in the past, is no, quantum field theory is about, and quantum gravity is what happens at the Planck scale, but this is at cosmological scales, and at cosmological scales that can't matter. And I say, what? I mean, you know, this vacuum energy is everywhere. Shouldn't I care about it? Shouldn't that affect something about what's going on with the way things gravitate if there's energy in the quantum field? Yeah, I don't know. But it is a question that I don't know the answer to. But from our point of view, if we're not worrying about GR, which we're not today, I mean, beyond this little diatribe I gave you about why I think dark energy is full of crap, we just ignore the 0-point energy. Okay? We're going to come back to that. What the calculus force? Come on. We'll come back to that. Right. So, let's talk a little bit more about the vacuum. We're going to come vacuum, we call 0. What is the mean of the field in the vacuum? Well, we have to take the expectation value of this. All right, so we're gonna, this is, well, let's put back in the time dependence here in the free field. So what is that? 0. Okay. However, what is the fluctuations in the field? Well, that's not 0, right? I mean, if I look at that, that is going to depend on something like the sum over k, whatever this characteristic scale is. And this is what? Well, I really should have had a k and k prime, but the only one that doesn't matter is a k equals k prime. So this is 1, right? So this is not 0. Can be huge as well. And this does matter. I mean, when you're in the vacuum, we say that we are not in an eigenstate of the field. There is uncertainty in the value of the field. And if we were to measure somehow what that value is at different times, we would get different answers. This does not have to commute with the number operator. So we call this vacuum fluctuations. And this plays a very important role in things like the Heisenberg force and spontaneous emission. Right. Now, I can look at a state with, say, 1 quantum of excitation. Okay, so for example, I could look at the state like this, which has 1 quantum of excitation in the mode K. Okay? We call a quantum of excitation in this field theory, of course, a phonon. That is a quantum of excitation of the field. In this case, the vibrational field of this molecule. And this phonon, we say, is a particle. In the sense that it's an indivisible object, 1 phonon. Can't have a half of 1. It's a quantum. Now, I don't have to have the phonon just in that mode. It could be in a superposition of modes. For example, suppose I looked at the state which is some superposition of these modes. Okay. That is to say, this is equal to this object. Right? I'm going to call this thing the creation of a phonon in that wave function. In other words, I've defined here a wave function, which is a superposition of those modes. And I've defined the operator A dagger of psi as the superposition of these creation operators. That operator, A dagger of that function psi, creates one phonon with this wave function. This, my friends, is called second quantization. We've kind of, and we'll talk about this, I want to talk about this a little bit more because it's very important. We've, in some sense, quantized the wave function. We made the wave function a kind of operator. We've associated with wave functions operators, and this is isomorphic. Any wave function of the phonon, I can write an operator which creates one phonon with that wave function. If C sub k was 1 for no, it would create it in the mode U sub k. Okay? So, the modes are like the wave functions of the phonons. They're a basis of the wave function. They're the energy eigenfunctions of the phonons. If I have a hard wall boundary condition, what do those wave functions look like? Well, we have the ground state, we have the first excited state, we have, I'm going to hate when we have markers because I'm going to come out with ink all over my hands every day, I know. But anyway, we have the second excited state. These are the energy eigenstates of a particle in a box. If I have a particle in a box, it doesn't have to be in this state. It can be in any superposition state. I can localize the particle at a particular position. How would I do that? Well, in that case, if I'm in a position eigenstate, I have this unnormalizable function, say it's localized at position x naught. That would be a particle localized at position x naught, right? Which I can write using my fancy schmancy completeness relation like that, right? This was the delta function relation, you remember that? That these were a complete set where I had this x prime, now I'm calling it x naught. But look at what these things, these are just the coefficients of the expansion. Right? So, if I look at this thing, well, I'm going to call this thing, I'm now going to let me define an operator just like I did over there with these coefficients. These coefficients times AK dagger. Okay, so this, what we just said, take the coefficients, weight them by the function. That is a thing that creates a particle at the position x naught. Okay? Now notice a close relationship between this thing and this. Let's look at this in the Schrodinger picture. Let's go back to the Schrodinger picture. Often is now. Okay. Notice that this thing is just this thing, but without that. And that we call the this operator creates a particle at position x naught. In other words, when I operate this on the vacuum, I have one phonon localized at x naught. This guy, one phonon localized in mode, or I would say in mode K. Yes, sir.
We know that photons are waves, right? So how can you imagine that they're localized?
What? Electrons are waves too. I would have to have a wave packet. You know, there's everything we learned about in quantum mechanics and not, this is, oh, by the way, this is a non-relativistic field theory because the speed of the, what is the, if I were to ask what is the speed of the phonon, what would the speed be? How fast does the phonon move?
Speed of sound.
Speed of sound, right? There's the phase velocity or the group velocity depending on how. So I can localize a phonon. I would just have to create a wave packet. I could localize a photon somewhat. It's a little bit of a trickier business that we'll get into. Photons are a little more tricky because of their vector nature and their relativistic nature. So, with this second quantized notation, I can look at, for example, if I wanted to ask what is the wave function of the photon here, what I have to do is I have to look at this in the position basis, right? But how do I look at this in the position basis? I have to look at the bra with the position eigenvector. When I operate this on the vacuum, I get a position eigenvector, right? So I'm going to look at the inner product between, which is for x. So this is the bra of creating a phonon at position x. I'm going to look at this with that. So this creates the phonon in mode K, and this creates the phonon at position x. This should be sub K, excuse me. Now how are we going to do that? Well, let's do a little aside over here. Let me look at the commutator between two operators, one that creates in the wave function psi and one that annihilates in the wave function phi. Let's say that psi is equal to the superposition of modes like this, and phi is a different superposition with a different set of coefficients. So this is equal to a sum over k prime. The commutator I have d k star ck prime, the commutator ak prime dagger. But this is that. And so this is equal to this, which is nothing more than the inner product of psi with phi. You see that? If I look at the inner product of these two wave functions, that's this. So, with that said, this is equal to this, which is ukx. The wave function of the phonon in the mode k is that function. Yes, sir?
Is there a reason you don't put the hats on these?
No, I'm sorry, I was lazy. I want hats on. Absolutely.
Okay, great, thanks.
Yeah. Yes, sir?
So, why are we considering only one particle?
Oh, good question. I'm just starting there.
Oh,
So these are just an example. I can think about one phonon and want to think about one phonon in any state I wanted. That's exactly the next step. Let's think about two. So, let's say I created a two phonons, one in mode K and one in mode K prime. I ask you now, what is the, let's say that K doesn't equal K prime. Otherwise we'd have to normalize it differently. What is the two phonon wave function? So there is the mode K, each mode, there's a K, has a, we just said for a single phonon in that mode, its wave function right here was this. Now I want to know what is the two particle wave function associated with these two particles, two phonons. One has wave function, so I want to look, I want to know the two particle wave function. What's your guess? Okay, so one of, so you might say yeah, so it's just a product state. Let's check. So, I want to know what the two particle wave function is. To do that, I need to look at the representation in the position basis of my two particle state. Okay? That's what I'm going to do. So I've got to look at the vacuum. I have to create a particle at position x1. Oh, that's the bra, so I got to do that. And I create one at x2. And now I have a dagger k prime and a dagger k acting on the vacuum. Is that clear? So this came from creating one phone, just like we wrote over there. This is the state. And this is the position representation written in terms of second quantized operators. So now, how am I going to evaluate this matrix element? Well, the way you always evaluate this kind of matrix element is you move the things that are annihilation operators to this side and things that are creation operators to that side so that you annihilate them. So I claim that this thing is equal to this, the commutator, right? Because when this hits the vacuum, it gets 0. And when this hits the bra of the vacuum, it gets 0. It's doubly 0. So I could just replace it by its commutator. Okay, so how do you do this commutator? Well, you bring this guy out first. And then I have to do it the other way around. Oh my God, everything is messy here. There's a K and a K prime. And then I have the commutator x2 with K. Sorry, 2 and prime, that's this guy. Then I bring this guy out at x1 and k, x2 and k, sorry. All right, what is this commutator? Well, it's the same one we had over there. It's the inner product of this. This is u sub k prime of x2. And this is u did I do this right first? Let's go more slowly over this.
Question.
Yes, sir.
Why are you allowed to go do what you just did? I'm not talking about the very last thing where you evaluated.
Yeah, no, I think I did that wrong. Let's go some more, so I think I made a mistake. Start, let me go more slowly here. We all agree this is right, right? Because originally I didn't have a commutator, and with the commutator, 0. So now I remember the following thing. A, B commuted with C times D is equal to A, B with C and D plus A, C with D with B, right? And this is equal to A, C B, D plus A, B, C, D. That's this first guy. And then I have to do the same thing here, right? So I have to do all those commutators here. Everyone see what I'm doing? This guy is C, A with D, B plus A with C, D, B. You agree with that? Yeah, that's what I gotta do. All right, you ready? So first, I bring this guy out front. That's this term. And then I get a dagger K with, so this is the ACB with D. That's the first term. Then I have this term. That's this guy, right? Stay with me here. Then we got this guy. I got to bring the A dagger, but oh, that's good. Because when A dagger hits that, I annihilate it, and the other ones. So those are the only terms that are left. And that's good. Okay. So, because when A dagger hits the bra, it annihilates it. Okay, so now what's this? That's the wave function u k prime and x2, right? Now what's left is this acting on the vacuum. But how do I evaluate that? Well, I just replace it by its commutator. Because going the other way would annihilate it, which gives me UK1. Similarly, this is UK of x2. And when I evaluate the rest of it, I get UK prime of x1. That's from the related term. So, with all of that said, that mess, that horrible mess, what have we found? No. That is not the two-photon wave function. What is the two-photon wave function? It's equal to UK of x1, UK prime of x2, plus UK prime of x1, UK, and I didn't somehow normalize this right, but I don't care, because it's the last class. Last chance. What can we do? That's what we got. So, what do you make of that? Any thoughts about why that actually is the two-wave function we should have expected in the first place?
Because photons are bosons.
Because these are bosons. Phonons are bosons. And this is symmetric under exchange. So if I switch the coordinates of particle 1 and particle 2, I should get the same wave function. And I do. When I created the state here, I created one phonon in mode K and another one in mode K prime. But who's to say which one is phonon 1 and which one is phonon 2? They are indistinguishable particles. And thus, the wave function should have symmetry under exchange, because who knows which one is 1 and which one's 2? Nothing said which one was 1 and which one was 2. So the wave function must be, that's why Manuel was supposed to give away the punchline. Like, no, let me surprise them. Well, anyway, you see what happened. Now, what is amazing is that the second quantized notation does all the symmetrization for us. We don't have to think about which one's one. We just know there are two identical particles, and it's already taken care of. Now, question for you. Where in the world did the fact that phonons, what if phonons were fermions? This would have gotten it wrong. Where did we, in some sense, quickly assume that these things were symmetric under exchange? Because we assumed commutation relations. We assumed that this was equal to this when k wasn't equal to k prime, because for two different modes, or no matter what, whether the same mode or not, this is 0. We assume that they commute. And that is an assumption that's valid when the underlying particles are bosons. If they were fermions, we would have to say that this was equal to minus that. And then we'd say they would anti-commute.
Where does it minus come from?
It's by assumption. It's when we write down the quantization, we have to know whether we're talking about bosons or fermions. And that is based on the spin statistics connection. So, what is the spin of the phonon? What is it?
Plus minus 1, 0.
Is it plus? Well, first of all, the spin is a positive number. First of all, is the spin an integer or a half integer value? It's integer, right? Because it's a boson. And what integer is it? It's 0. It's spin 0 because it was a scalar field. It had no notion of rotation direction. So the phonons, because they were a scalar field, are spin 0. And thus it was perfectly fine to assume commutation relations rather than anti-commutation relations. Yes?
What happened if we did assume anti-commuting the scalar field?
Well, it wouldn't be correct. I mean, you can't, we know that the contradiction, the spin and exchange statistics are intimately related. The proof of that comes from Lorentz invariance. So it's something that we don't prove until we get to a more, doing Lorentz invariant quantum field theory. But for the moment, we just take that as law, that we must have symmetric under exchange for integer spin and antisymmetric under exchange for half integer spin. And since this is an integer spin, we have to have commutation relations. Yeah?
But they have different energies, right? The two phonons. How are they indistinguishable?
We still don't know which one they are. We can't, which one has which energy. Does phonon 1 have energy, h bar k, and the other one have it? Which one do you want it? There are two energies, h bar k and h bar k prime. This guy, let's say this was, a microwave, and this one is a gamma ray. Does phonon 1 get to be the microwave, and photon, and this one get to be the gamma ray? Who gets to be the gamma ray? I can't tell which one is which. So we have to say that the two photon wave function gives them both the chance equally to be the gamma ray. Right? Now, as you know, the question of whether the quantum statistics play any role in calculating the probability is whether or not the actual particles overlap in space. If they are localized differently, it doesn't make any difference. The exchange term in the probability density is 0 when there's 0 overlap of the wave function. So let's say I have two ions. One is trapped over here and one is trapped over here. Now I have ion 1 and ion 2. I have to symmetrize the wave function, but who gives a crap? I just say there is the ion in this trap or the ion in that trap. Whether I call it ion 1 or ion 2 makes no difference. And if I write down a symmetrized wave function, that two-body wave function, if I look at the square of this wave function, there will be an interference term. But if wave function 1 and wave function 2 never overlap, then interference term is 0. So the statistics of indistinguishable particles only matter if the particles overlap in space. If they don't, if there's no probability of finding those two particles at the same place, I can forget about exchange statistics. Which is why when we think about a gas of atoms, we never worry about the fact where they're bosons and fermions until we have to. When we cool them so that their Broglie wavelength gets big enough that they have a high chance of being in the same place, then we can think about Bose condensation or something like that. But otherwise, we don't have to worry about it. All right. I just want to begin to introduce how we would now apply this in the context of the electromagnetic field. We'll just begin the discussion. And we'll finish it next week. So, we have the electric field and the magnetic field. Looks like we have 6 components here to worry about, right? We got the X component, the Y component, the Z component. So unlike our scalar field, now we have this vector field with 6 components. Do we really have to worry about 6 components? Well, first of all, we're talking about the free field. To quantize it, we're thinking about this in the absence of charges. So that we call it a free field. No interaction with anything in the same way that our elastic rod didn't interact with anything. Do we really have 6 independent fields? No. Because, of course, we have Maxwell's equations, which relate seemingly, right? And for the free field, we have Faraday's law, and you have to live with Sanskrit. Because I don't deal with epsilon knots and mu knots. Now, of course, so that means these guys are interrelated, right? These and these. And the way that we, of course, deal with that is instead of thinking about the fields, we think about the potentials. We can think about this in terms of the 4 potential. We have the scalar field, or the scalar potential, and the vector potential. So this looks like we have 4 degrees of freedom rather than 6. Or do we? Well, we know that there is gauge invariance. So let us remind ourselves how, of course, the magnetic field is the curl of the vector potential, and the electric field is 1. So we got, this is equal to the time derivative of the vector potential and minus, right, the scalar potential, right? So, gauge invariance tells me that actually there is an extra degree of freedom, some extra degree of freedom here, because I can shift both the scalar and vector potentials in some way and not change the physical theory. In other words, if I take the vector potential and I just add to it the gradient of some other scalar field that we call the gauge field, and simultaneously shift the scalar potential in terms of the time derivative, I don't change anything. So there's some additional degree of freedom. Now, the way to think about this is the following. Now, this is something I'm not sure you learn in your E&M courses, but you should. It's something called Helmholtz theorem, which says that any vector field can be decomposed as follows. Let's look at the vector potential in particular. I'm going to call this a part I'm going to call A parallel, and I'm going to call a part I'm going to call A perp, where A parallel is irrotational, meaning its curl is 0, and A perp is solenoidal, meaning its divergence is 0. Any vector field can be decomposed into a piece that has 0 curl and a piece that has 0 divergence. Anything. This is called Helmholtz theorem. You guys learn this? Yeah, good. Now, what this says is, of course, the B is purely transverse. It has no solenoidal piece, because the divergence of B is 0, right? So, B is equal to the curl of the transverse part. The longitudinal part plays no role, it has 0 curl, okay? E breaks up into 2 pieces. There's a part of E that is transverse and a part of E that is longitudinal. Right? Just breaking it up into those 2 pieces. This part has 0 divergence. This part has 0 curl. But if I look at the divergence of this, I'm going to take the divergence of this term. Well, that's equal to 0, right? Because del dot E in the free field is 0. And del dot E is del dot E perp plus E parallel, but the divergence of E perp is 0. So this is from Maxwell's equations. So, what can we say from this? What we can say from this is that as far as the transverse part of the field goes, there's no A parallel term, there's no there's only an A perp term. From the point of view of the longitudinal part, there's a constraint, which says here that the Laplacian of the scalar potential is equal to this.
Did you need to elaborate on that?
Oh, I did. Thank you. Sorry. The divergence of this, that's important. So, what this equation tells us is that the scalar field in the theory is not dynamically independent. Does anyone know the solution to this equation? Given this function of time, what is the solution to this differential equation? Well, this is like a Poisson-like equation, right? And the solution to this says that this field at this time is just the integral over all time, whatever this thing is at the initial time over x minus x prime. Right, if this was whatever this thing is, I put that in and I integrate over all space. So, what this tells me in this equation here is that the scalar field is not an independent dynamical variable. The scalar field is a function of the parallel part of A. And the parallel part of A is irrelevant because it plays no role in the dynamics here. This is a complicated business associated with the fact that we have this gauge invariance in electromagnetism. And somehow we have to get rid of that degree of freedom by making a choice of what to take for A parallel. The choice of A parallel determines the gauge. And the typical way we quantize the field is to choose the gauge such that the divergence of A is 0. That is to say, we choose A parallel to be 0, because it's irrelevant. This is called the Coulomb gauge. And in the Coulomb gauge, we're left with these equations. The equations that tell me that E perp, and put together over here, this tells me that the curl of E is equal to minus 1 over C dE dt, and the curl of B is equal to plus 1 over C dE dt. And everything is transverse. And the longitudinal part is 0.
For the E's and E's and K's.
One of them is B. This is Faraday's law and Ampere's law. All right, I want to conclude with the following question for you. Is the photon a fermion or a boson? We know it's a boson, but how do we see it from these equations? Well, it's a complicated business. The components here are, we're talking about our vectors in three-dimensional space. So they're three-component vectors, and even be related, doesn't matter. Which means three components is what's kind of spin. Spin one, right? Because I have three, it's a spinner with three components. There's 2 times the spin plus 1 components. So this is a spin one theory. Therefore, it's theory of bosons. However, it's a complicated spin one because we have this constraint. And this constraint is going to be important. It says that the direction of the vector is constrained in some way. And that constraint will tell us that in fact there's only 2 polarization states that are allowed. So even though it's spin one, not all directions of the vector are allowed. And that's intimately related to this. So it's a very complicated theory. It's a spin one, but it only has 2 possible polarization states, even though it should have 3. We'll come back to that next week. All right? Say goodbye to physics and say hello to Titus. Have a good weekend, everybody.